Problems that pipelining introduces. What do we call those problems? Hazards. How many hazards? 3 of them. Control, structural, and data. Structural hazard means that 2 instructions in the pipeline want to use the same structure at the same time. That's a problem. How do you fix them? Well, you design your pipeline so that 2 instructions don't see the same structure in 2 different stages of your pipeline. What if you can't do that? Well, we won't actually talk about that in this class all that much, but you would serialize those instructions through that shared structure. So you'd have some way of ordering them, program order usually. Earlier instruction that you fetched is the one that goes through first because it's earlier in the program, so you want it to result first. And you let them go one at a time. Control hazard means that you have an instruction in your pipeline that you don't want in your pipeline. You have fetched the wrong instruction according to how the program should execute based on all of its inputs. So far, we've identified branches as introducing a control hazard. Jumps do as well, but they're very similar to branches. At some point, we'll probably also talk about exceptions. Exceptions introduce control hazards as well. Exception is the program did something exceptionally bad. And then data hazards. Data hazard means that your pipeline is operating on the wrong data. Generally, what this means is you read the wrong value from the register file. And we've got 2 ways now to correct it. Wait, and forwarding. Forwarding the value, plucking it from somewhere in the pipeline where it already exists, and passing it forward in the program, which is backward in the pipeline. This way is forward in time, forward in the program, backward in the pipeline. Be surprised how common it is to get forward and backward and higher and lower confused in computer systems. Load use hazards are a specific kind of data hazard where a load instruction is followed immediately by an instruction that uses its loaded value. The data hazards in our pipeline come from a certain kind of dependency, data dependency in the program called true dependencies. You remember what the other 2 dependencies are? Right after read, also known as anti-dependency, and while, or output dependency, right after write. For the time being, we don't have to concern ourselves with anti-dependencies or output dependencies because the structure of the pipeline ensures that we serialize writes down here at the end of the pipeline. So our writes are going to happen in order of program order. If somehow we allowed instructions to execute out of program order in our pipeline, and they could write values out of program order, then we would have to deal with those dependencies. That kind of out of order execution behavior, that's how high-end modern processors, by high-end I mean server and desktop and smartphone processors typically. When I first came here, they said, you're going to teach the undergraduates the same thing as the graduates, just a little different, but the graduates are going to learn about this complex. So I tried to teach out of order processors. It was rough, hard, and a bad reputation. That's okay, because my class size is smaller. Okay, I want to continue to increase our understanding about how data hazards are really dealt with. And I also want to add another layer of knowledge onto how we deal with control hazards. It's in more detail than we've been doing it. So we're going to get our pipeline here, and then we're going to stick forwarding in here, and then we're going to do some things to help us mitigate control hazards. As usual, the caveat here, I may mess some things up. Hopefully, if you know them, you can correct me, and if not, hopefully I correct myself later, and if not, conceptually, we'll all be okay. I don't always admit that. I want you to know I'm human too. I think you knew that. There's the instruction. There's the program counter. Split the instruction up, just send wires lots of different places. ALU, then produce the second signal, calculate the branch target, program counter, plus immediate, shift to left once, 0 signal. And the selector for this mux. Memory stage, my data memory, is my address or write value. ALU result, it's got to go around, figure out what my write back value is. Then to reg, control signal coming from. That's our pipeline, if I'm missing anything. I mean, for our basic pipeline. This is where we begin with the program counter. The very first thing conceptually we do is we read, which is an address, and we send that address to the instruction memory, which gives us an instruction. That's value 0. Ignore it for right now. When the pipeline is full, let's just assume the pipeline is full. At the same time, we're reading from the program counter. We're also reading from this interstage buffer. We're also reading from this one. We're also reading from this one, and we're also reading from this one, all at the same time. Which means we're starting our instruction memory access. We're calculating our PC plus 4. We're reading 2 registers. We're generating an immediate, and we're decoding the output. We're picking a register value or an immediate. We are figuring out what our ALU is going to do. We're shifting left the immediate by 1. All at the same time. All this is happening. All at the same time. We're also, maybe, starting a load or store, depending on the control signals here. We're also ANDing the branch control signal with the 0 signal coming out of this interstage buffer. All at the same time, all the time. All of this. We're also selecting one of these 2 inputs to send to the register file. That's all happening all at the same time, a short amount of time after the clock tick, based on the delay it takes to latch new values into the registers, because that's what happens at the clock tick. And then for those new values to come out the other side of the registers, traverse their wires to the next component, or really the first component, they hit in parallel in each stage. All that's happening at the same time, although I've drawn it and explained it always left to right. And you asked me about arrows. I can do some arrows too. Arrowheads. Generally, everything's going this way, except these backwards. Mostly going left to right, top to bottom. Why left to right, top to bottom? Because that's how Western civilizations have decided to read and write. I don't know of any civilization that reads bottom to top. Maybe that helps, maybe it doesn't. Let's start with hazard detection logic, because we know we need it. We can't have a write processor without it. I'm going to make myself some space here by erasing the word decode, because you know what it is. You know the names of all the statements by now. Hazard detection logic is going to go here. We need our hazard detection logic to squash the instructions that are in the pipeline in case there was a branch. Was there a branch? There it is. Somewhere in there, there's logic that checks if this is a 1. It's a really easy logic. And if it is, squash, also known as flush, the instructions that are coming behind that branch in the pipeline. How are we going to do that? For now, we'll do that here. What I'm going to do here, I'm going to put all 5 of these control signals together. Wires, 5 wires are now 1 line on the drawing, 5 wire bus. So then I can mux it in one place, out the other side, 5 more wires. Then my other input to my mux is 5 zeros, so that all 5 of my outputs will be zeros. Control it from here. What does that mean? Well, it means my hazard detection logic sends a 1 here to this mux. That's going to replace the control signals coming out of this mux, make them into zeros, which means in the next cycle, this instruction is not going to read or write memory. 2 cycles from now, this instruction is not going to write to the register file. It has no visible side effect on the processor state. It doesn't write to any of the stateful components of my processor. Stateful components are things that can hold a state that store values. That'll allow me to squash the execute stage. I'm going to label this ex.flush. Flush or squash synonyms. I got to do the same thing here. I'm going to do it the same way. So I'll put a mux here. I don't have enough space for my mux. My input's going to be 8 bits and zeros. This time I'm just going to write it 0. Control it, decode.flush signal. Squash, whatever instruction be in decode. And already sent the wrong PC here to instruction memory to fetch it. It's too late to fix that because I can't write to the program counter. So I have to squash whatever's coming out of this instruction memory as well, setting things up ahead of time. And that's my instruction fetch.flush. Flush or squash the instruction under the assumption that a zero value opcode is going to be interpreted properly by the control logic as a no op. That's our hazard detection logic. Gives us the ability to squash or flush multiple stages of our pipeline, replacing them effectively with no ops. I promise you, this is all in the book. All you gotta do is read through it like 10, 15 times. And I'm trying to provide enough support structure for you to be able to approach that 10 to 15. So far, so good. Now we have a functionally correct. No, it's not yet functionally correct because we gotta stall if there's a data hazard. How do we know if there's a data hazard in the pipeline? Well, we know because there's an instruction here that's going to write to a register destination. It's this thing right here is my read-write signal. Probably label that. That's how I know this instruction is going to write to the register file. This is where it's going to write. It's my RD to detect a data hazard. I'm just going to expand my hazard detection logic with some additional capabilities. I'm going to do it in the same blob. Why am I going to do it in the same blob? Because I only have so much real estate to work with. In reality, we can split this up inside there. What I need to do inside this hazard detection logic is I need to compare the read-write signal of my execute stage with the destination register index right here. So the read-write signal and the destination that it's going to write to are now available to this thing. And now it just needs to know if I'm reading from the register file or where I'm reading from. And you can send it the opcode so that it can tell, well, this is actually an instruction that cares about what it reads from the register file. Oh, now we need the instruction here. You install it here because it's reading from a register source. One of these two register sources that it's reading from matches this destination, and that destination is going to be written. So we got to wait. How do we wait? We stall the decode stage by preventing writing to the IFID buffer. So we're gonna disable the write. Well, we're gonna send it to 0. So that'll be our stall. And if we stall the instruction here, we have to stall the instruction here because it can't go through. So we got to replay it, which means we got to prevent the PC from being updated. Do that the same way. Stalling the PC exactly where it is. Stalling this interstage buffer. So on the next clock tick, I'm going to fetch the same instruction. I'm going to decode the same instruction. Now I have to introduce a bubble into the pipeline to replace this instruction moving into the execute stage. And if I'm going to make a copy, if I'm going to repeat this instruction here, I can't just let it keep going. I got to replace it with a null. We already know how to do that. Insert this flush signal on a stall as well. So now on the next clock cycle, what happens? A no op moves into here. That instruction, the one on which this is dependent, moves into the mem stage. Now we haven't waited long enough, so we just repeat that again. It's the exact same thing to stall again. We can just stall again, install again, until we wait for that write to happen for the dependency to clear. We also have to be able to detect this dependency situation if it comes from here as well. But I'm not going to do that. Why am I not going to do that? Because we're going to jump right over that to forwarding. What is forwarding? Data forwarding or value bypass is taking the ALU result or the memory result, passing it back in the pipeline. When do we do it? When the instruction that's here needs it. We actually get a little bit lazy. We defer that by 1 second because we don't actually need it till here. So we're going to detect within our execute stage that the instruction here in execute needs the value produced by this instruction or this instruction. That happens to be extremely similar kind of thought process as what we needed to do to stall. We're just doing it here instead. By convention, we're going to do it down on the bottom. So we're going to add here, and this forwarding logic needs as input the destination registers from here, as well as whether they actually are going to write to the register file. And the sources, they're right here, the RS1 and RS2 indexes. Well, we don't currently have those. And we need them in the hazard detection logic. We're also going to need them in our forwarding logic, which means we gotta route these over this way. Just going to drop it off of this main trunk here and say same things as here. I could have connected them from here as well, but that would have made more lines than this here. RS1 and RS2 go into our forwarding logic so that we can compare where this instruction reads from and where these instructions write to. Well, that means we need to know where they write to. That's this right here. I'm making myself some more space again. So here's the RD of the instruction in the memory stage. Here's the RD of the instruction coming out of write back. It's written along the bottom already, so I'm just going to, that's RD. Put some arrows. So this coming in here, that's my write back dot RD. This one right here, well, that's my mem dot RD. Technically my EX/mem buffer value of RD. So I got my destinations. I also need to know if they're going to be written. Right there, I got my write back read write signal. Even however cleanly I can write it is impossible to read. So take my word that that's what write back read write. But that's what that is. I mean, you can see that that's what that is. I need the read write coming out of the mem buffer here, the EX mem buffer. I'll drop that down. So there's my mem.read write. So now I know where and whether the instructions in the memory and write back stages write to the register file. And I also know where the instruction in execute read its inputs from. Now I need outputs and a way to select forwarded values. I got all my inputs to figure out, do I need to forward? Now I have to have a way to forward. I am going to forward values to replace what I read from the register file. Add a multiplexer here, two multiplexers. One for RS1, one for RS2. I'm going to either pick what I read from the register file, or I'm going to pick something from further down the pipeline. Now there's two somethings I can pick. The ALU result coming out of the EXMem buffer. So there's my value from the ALU result coming into this here. I'm going to make 0, 0 be don't forward. And then the value that's going to get written to the register file in this stage, which is this value right here. So that's how I get the values to where they got to go. And then my forwarding logic tells me what to select. Forwarding logic outputs here. We're going to call this one forward B, and this one forward A. Going to pick either what I read from the register file or something forwarded from down the pipeline. We can't solve all data forwarding problems, all data hazards just with data forwarding. We can't solve the load use hazard. For a load use hazard, we also have to stall the pipeline for one cycle to give enough time to read the value from memory. We do that here in our hazard detection logic. Our hazard detection logic here is going to look and see that, oh, this instruction is reading from the destination registers, that this instruction here is going to write to from a memory load. We have to add one more thing here in our hazard detection logic, which is we have to know this is a memory read, memory load. So we send the memory signal of the instruction in the execute stage back here at the hazard detection logic so that the logic here can say, oh, there's a memory here. Its destination is the same as one of these sources. Therefore, I have to stall decode for one cycle to give enough time for my load instruction to get into memory and read the value that I need so that I can forward it. Next cycle, my load is here, my bubble is here, that dependent thing is there. I let it read the wrong value from the register file. The next cycle, my load is here. I can pluck the correct value from here, and that's what my forward logic will do. It'll pluck the correct value. We got 2 minutes. Blow your minds. Another way we deal with control hazards is to reduce their impact by reducing how many cycles we have to stall for them. We can do that by pushing this branch instruction all the way into here. How's that going to work? Better take a picture now if you want one. I only got 1 minute left. This is going to be fun. Fun. How do we do that? We put all of our branch logic stuff in here. So I got my AND gate here. I got my branch signal comes from here. I got a comparison of the values coming out of my register files. I'm going to compare if they're equal. If they're equal, this is now my branch signal. And then I need a way to calculate my branch target. Well, I got my immediate. I just take my immediate here. I do my shift left by 1 here. And then I add it here to my program counter. There's my branch target. Now when my branch is here, I need a way to forward values from here and here back to here. So I actually need some additional forwarding logic here. Add muxes here. And these muxes are going to have forwarded values from down the pipeline. Oh, shoot. It came from up here. That's okay. Forwarded values coming from further down the pipeline. And it needs to be able to compare the RS1 and RS2 of my branch instruction with the destination registers of instructions further down the pipeline to know if I should use the forwarded value from further down the pipeline so that I can forward from execute or memory back into decode. I don't have to forward from right back into decode because I read from the register file. I write to the register file in the first half of the clock cycle. So that part's safe. So by doing that, I can push my branch into here. And then when a branch is taken, I only have to squash this instruction. So it reduces how many instructions I squash by 2. Cool. Have a great day. We'll go over that again. Don't worry. I just wanted to plant that seed for you.